Okay, it's just after 2 p.m. Eastern Time, so I think I'll just get started. I'd like to welcome you all here again to our webinar series on SOLAS for Missing Data Analysis. This is the final webinar in this webinar series. Thanks for everyone who's been attending all along, or if it's your first time attending, welcome. My name is Andrew Grannell. I'm a senior statistician here at Statistical Solutions, where we develop and distribute SOLAS. I'm also here with my colleague Eoghan Murphy, who's a statistician with us. And the format for today is, if you have any questions while I'm presenting, just put them through the text box there in the GoToMeeting window. And Eoghan will be dealing with those questions as they come in, and I'll be taking questions throughout the webinar and at the end as well. So we've had some internet connection issues over the last few days, so if the images slow down while I'm talking, again, just give us a comment through the text box to let us know, or if the sound quality is not very good, again, just let us know and we'll try and rectify it before the end of the webinar. First, I'd also like to say happy 4th of July. I hope you all had a nice holiday last week and enjoyed it. If it's anything like how we celebrate our St. Patrick's Day, I'm sure it was a great time. What I'd like to do today then is recap on the entire webinar series. So we had 6 webinars in this series, and this is the 6th one. Then we'd like to talk about sensitivity analysis today. So what exactly is sensitivity analysis in multiple imputation? Why do we do sensitivity analysis? We'll explore some in SOLAS, and then we'll go through some any questions and comments at the end. And also there's going to be a recording of this as well as a recording of all the other webinars. So if you don't have a question now, if there's something that's on your mind, you can watch the recording of the webinar on YouTube and ask me questions via email or anything at a later time. So what did we cover so far? So in this series we discussed defining missingness. What types of missingness are they? Monotone missingness, or is it non-monotone missingness, and how do we treat those in different ways? We also looked at the different the different types of missingness were missing completely at random, missing at random, and missing not at random. And then we looked at the different missing data patterns, which were non-monotone and monotone, and how you deal with those in the process of missing data analysis. We also then looked at various different approaches to multiple imputation and different models. We discussed the predictive model-based method, Mahalanobis distance matching, propensity score matching, predictive mean matching, and our combination method. We also did some pre-imputation exploration techniques, such as our scatter plots, our margin plots, our missing data pattern tables. All these were very handy, useful methods to just explore the missing data before you actually went into any analysis. And we also discussed various examples of doing post-imputation analysis and how you should approach analyzing your imputed data. So what we're here for today is sensitivity analysis. So what is sensitivity analysis? We feel it's probably the most important part of the missing data analysis part. And it's relatively a new topic. And it's gaining a lot of traction in many industries and many fields. The literature is constantly evolving, constantly updating. There's new methods always being incorporated, and a lot of that is to do with the increase in computation power and computation memory. So now we can do a lot more with computers. We can do a lot more calculations a lot faster. So, and when we're dealing with imputation, you're creating multiple data sets from one data set. So when you used to be doing one set of analysis, now you're doing many analysis, and sometimes you could be doing them concurrently, one after the other, or whatever. I just have a picture here on the right-hand corner of the report that the National Academy of Science and Statistics did. They were approached by the Food and Drug Administration, the FDA, to put together a report on recommendations on how to approach missing data analysis and the prevention and treatment of missing data in clinical trials especially. But I think this is a very good report, and it can be extrapolated to any other industry, not just clinical trials, but this report is especially focused on that. And of that report, I think they had 18 recommendations ranging from how to reduce your missing data to how to actually analyze your data set with the missing data included. And two of the recommendations included sensitivity analysis, and I'll just quote one here. Sensitivity analysis should be part of the primary reporting of findings from clinical trials. Examining sensitivity to assumptions about missing data mechanisms should be a mandatory component of reporting, and that is the missing at random or missing completely at random or missing not at random. They're the mechanisms. And then they also went on to say when substantial missing data is anticipated, auxiliary information should be collected that is believed to be associated with the reasons for missing values and with outcomes of interest. So they do mention sensitivity analysis in their report, and they make a recommendation to the FDA that when they're putting together their guidelines on dealing with missing data, that they should consider sensitivity analysis. Okay, so sensitivity analysis, exactly what is it? It's pretty much a stress test of your assumptions. You're trying to explore how volatile the values are that you've imputed, and also how does that affect the data. So how have you changed the outcome of your analysis based on the imputations you've made? So you normally do your normal complete case analysis, or however you would have dealt with the analysis before. You do that anyway, and then you'd also do your missing data analysis and always compare and contrast across on how things have changed and how much have they changed. Several aspects always have to be investigated. There's four main areas that I'd like to touch on today. There's the distribution assumptions. So when you're looking at distributions of variables, there's outliers and influential observations. You're looking at your assumptions about missing data, and then the information that is in or not in the data. So when we're talking about using informative or non-informative priors in a model, or bringing in any auxiliary data, anything that could help you uncover information about the missing responses. So I'm just going to take a very simple example here. If we take the distribution of an overall population for a certain variable here, we see it's just a normal curve. And say, for example, we know this is what the overall population looks like for a specific variable. But when we do our study, we only get a 50% response rate. And the 50% that we got was in the right-hand side of that curve. And the 50% non-response is in the left-hand side of that curve. So it just looks like this. So we have a direct, and this is an extreme case, but we have a direct split in the respondents in our study. So what is the correct, or what is the appropriate measure to use to describe the group of respondents? Do we take the lowest value in that group, which would be closest to the actual mean for the population? Do we take the median or the mean? What do you do? And in the complete case analysis, that's what we are doing. We're looking at the distribution of only the respondents. So, and this is quite a tricky task for any researcher dealing with real data and missingness. Also, how do we define an outlier? If you've got missing data in your population study, how can you define something as an outlier? It could be closer to the true mean just based on the sample you've taken. How do you know that outliers are actual outliers, and how do you know that they're not actually close to the true mean? It's just you have been unlucky to get a sample that has mainly the outliers and not the actual true mean. So how do we define outliers that are outliers? So I've circled these that look like outliers because they don't conform to the actual data points that we've observed. But how can we say that these values are actual outliers? For all we know, one of those outliers could have actually be this person right here, which is very close to the actual mean for the overall population. But because it's an outlier from the data that we've collected, it's hard to tell. These are all things that are unknown to us. So how do we define missing outliers and missing data? We can use model-based methods of imputation, where we can talk about trying to predict what that value was. So we can use the predictive model-based, predictive mean matching, or a combination method, which includes modeling in there too. If we just want to do a broad comparison across different the different types of imputation methods in SOLAS, there's two main types of methods in SOLAS. There's the model-based methods and there's matching-based. So we have two matching-based methods and we have three model-based, so that's 5 in total. So the matching-based, which would be propensity scoring or Mahalo-Novus distance matching, they are insensitive to nonlinearity because they're just purely looking at matching, finding an appropriate match. It works best with overlap between the outcome variable y and the covariates, and they perform better if the correlation is high between the outcome and covariates. Whereas if we contrast that to the model-based methods, where we're looking at linear modeling or logistic regression modeling, the performance is not as strong when it comes to levels of nonlinearity. If nonlinearity is high, the regression modeling can get into a tricky spot. But if there's not overlap between the independent or the outcome variable and the covariates, then we can use these models as predictors, and the models are not affected by correlation between y and the covariates. So now I'm going to look at sensitivity analysis in SOLAS. How do we do it? I'm just going to scratch the surface here again. We can run our multiple models, the 5 models I just talked about, 2 which are matching and 3 which are the model-based methods. You can run your models, multiple models on the data and compare the outcomes. We can create several imputed data sets for each method. Then we can investigate why or if methods are performing or not performing compared to other methods. And then we can make an informed decision on which methods to select and which data to choose for the actual, to move forward with the actual analysis, and then base our inferences on. So eventually we need to select a group of data sets that we're going to perform our analysis on. Again, when you're incorporating multiple imputation, we're not talking about doing analysis on one data set anymore. So we're talking about doing our multiple analysis on multiple data sets. So I'm just going to run through a brief example in SOLAS. And now just let me know again if there's any issues with the screen or with the speed or the difference between the audio and visual. If there's any issues, just let us know. So I'm just going to close up this and go open up SOLAS. So, and if you need to zoom in, if the screen is too small now, if you need to zoom in, there's a zoom function on the GoToMeeting window. So most of you recognize this. This is the SOLAS home window where we can open a new data set, create a new data set, or open an existing one. There's a script language feature that we can avail of. If you run an imputation, you can go back and alter the code to calculate whatever you like. And there's quite an extensive help manuals there to help you that. So I'm going to open up a data set now called treatment missing. And here we have a spreadsheet format of a data set where we have the variable names across the top and the cases in the rows. And this data set has 9 variables and 188 cases. And what this data set is, it has various measurements of the patient's profile, such as their age, their height, and their weight. And then we have this categorical variable treatment, and basically it tells us if the patient was treated or not. And then we also other measurements, such as cholesterol values and dosage levels of 3 different drugs. So this is quite a very basic data set on a clinical trial. or a public health example, but quite basic just for this example. So as we've seen before, you can just analyze the missing data pattern just to see the extent of the missing data in the data set. Here, where the blue cells represent missing data points and the white cells represent observed data points, I can collapse this down to a more readable table where we can see out of the 188, I have 144 complete cases, 2 cases with this particular missing data point, 42 cases with this particular missing data point, and so on. And then I can also split this into the monotone and non-monotone pattern. So here the green cells are the non-monotone and the red is the monotone. So I'll be imputing these values first, and then I'll be imputing these. So that's the missing data pattern. So now we're kind of aware of the extent of the missing data. We have 151 full complete cases out of 188, so that's not too bad. So what I'm going to do is I'm going to run all 5 imputations, and I'm going to compare the results of a simple t-test across all 5 data sets. Now, what I'm going to do first is I'm going to do the original t-test, and I'm going to compare cholesterol levels between the treatment groups, patients who were treated and patients who weren't treated. And I'm going to see the null hypothesis is that the mean difference is 0, so I'm going to see if there's a difference or not. And this is a complete case analysis, so we're just looking at the observed data and not including the incomplete case. So I could just select my outcome variable as cholesterol and my grouping variable as treatment, click OK. And then we have the output window that gives us a table for the number per group, the mean for each group, standard deviation and standard error, and then we have a simple test statistics table. We can add more, there's options to add more to the output, and we can also do some stereo plotting features here. But as we can see here, the mean value for the no group is 222.8, and the mean value for the yes group is 243.9. So the yes group has quite a higher cholesterol level than the no group, and you can see here that with a p-value of less than 0.05, there is a significant difference between the 2 groups. So this is before we do any multiple imputation. So now I'm going to do multiple imputation. I'm going to do the 3 model-based methods first, the 3 regression-based methods. So I'm going to do the predictive model-based. I'm going to use age, height, and weight as the fixed covariates. So these are the variables that are going to group the patients. So people with similar height, with our height, weight, and age are going to be used. And I'm going to impute the 4 incomplete variables: cholesterol, dose 1, 2, and 3. And I'm just going to run 5 imputations for to keep it simple again here. I'll click OK. Now, here we have a new window opened with the complete variables here. So the red values are the imputed monotone values, and the green values are the imputed non-monotone values. And at the bottom here we have a tab, 1 for each of the 5 data sets. So here I'm going to do the t-test again on the newly formed 5 data sets. I'm going to use cholesterol as the outcome variable and treatment as the grouping variable. Click OK. And now you can see that the no group has increased and the yes group has decreased, the mean value for each group. We also now have, instead of 141, we have 188. Instead of 76 per group, we have 94 per group. So we've increased our sample size. We've included more people. And you can see that the p-value now has gone up above 0.05 to 0.09. So now this model is telling us that there is no significant difference between the 2 groups, treatment groups. So now I'm going to run this model. I'm going to do a new imputation using the predictive mean matching model, which is similar to the predictive model based, except instead of imputing the model values, we actually impute observed values that are close to the model value. So again, I'm going to use the same fixed covariates, age, height, and weight, and I'm going to impute the 4 incomplete variables. I'm going to do 5 imputations, click OK. So now I've got 5 new data sets for my predictive mean matching model. And again, I'm going to run the t-test, cholesterol comparing treatment groups, click OK. And now here's my output window for the 5 data sets for predictive mean matching. And again, you can see that the no group has increased to 231. The yes group has slightly decreased. And again, predictive mean matching is telling us that there's no significant difference between the two groups again. So that's 0.2 value there. So that's predictive mean matching. Run this again for the propensity score predictive mean matching Mahalanobis distance combo method. Set up the same imputation model again using the same fixed covariates. 5 more data sets. So now I've got 15 data sets created so far. 5 more data sets, t-test, cholesterol, treatment, click OK. New output window. And again, this model is telling us no significant difference again. So the no group has slightly increased, yes group has decreased, and we're saying that there's no significant difference between the two groups. So that's 3 models. The 3 regression model-based methods have told us no difference between the two groups, the treatment groups. So now I'm going to use the 2 matching methods. So that's propensity score and Mahalanobis distance. I'm going to run these 2. Set up my imputation model again using the fixed covariates and my variables to impute. 5 imputations and now 5 more data sets. I'm just going to run my t-test again. And now you can see that the no group has gone slightly increased, but also the yes group is slightly increased, and our p-value from our t-test is telling us that there is significant difference between the two groups, a p-value of 0.01. So now this is a different result to the regression model-based method. And finally, just to finish off, I'm going to use the Mahalanobis distance method. Set up my model again. Click OK. 5 more data sets. So now we've just created 25 data sets in SOLAS. 25 imputed data sets. 5 for each model. And now the Mahalanobis distance matching is telling me for data set 1, it's not significant. Data set 2, it is significant. 3, not significant. Data set 4, slightly just below 0.05, so slight, just below the threshold value, and again below the threshold value. So this is not a clear-cut case, and what you would do here is you would run more data sets to get a better understanding of the distribution of the imputed values, which I'll just cover in a second. But as you can see here, predominantly the regression model-based methods have resulted in a not significant difference between the two treatment groups, whereas the matching methods have produced a significant difference between the two groups. So I'm just going to go back to my slides here. So a summary of this example will show you the predictive model-based, predictive mean matching, and combo method. All these have returned, these 3 tests have, or these 3 imputation models have returned a greater than 0.05 p-value, which would mean there's no significant difference between the treatment groups. Whereas the propensity score and the Mahalanobis distance said yes, there was a difference. Now the Mahalanobis distance wasn't as clear-cut because 3 out of the 5 data sets had less than 0.05 p-value. So what you'd have to do is increase the number of imputations, and you'd have to examine the distribution of those values to see how volatile that method is. So next what you'd have to do is you'd have to tick your boxes here. You'd have to say, Well, the regression method differs from the matching method. So you have to check the properties of each method, which I went through earlier, and you have to see, is there overlap? Does enough overlap exist? Is there linearity? Does the linearity exist? Is there a correlation between the outcome and the outcome variable and the covariates? And in this case, the way I set it up was there was no correlation. There was low correlation between the outcome variable y and the covariates, and also there was a lot of there wasn't much overlap between the outcome variable and the covariates as well. So that means the matching methods would not be appropriate in this scenario, and that the regression models were more appropriate. So then what you would do is you take the 3 regression models, predictive model-based, predictive mean matching, and the combo method, and you'd use those to create imputations and run your analysis on all of those new data sets and make your inference based on those results. So that was just a roundup. I hope that that webinar was quite helpful for you, and just to kind of scratch the surface on the area of sensitivity analysis with missing data. And that concludes our webinar series for this term. The next webinar series will be beginning sometime in the autumn or winter this year. Again, if you have any suggestions of anything you'd like to see in our webinars, please let us know by simply emailing us or contacting us in any way. Upcoming conferences that we'll be attending the Joint Statistics Meeting, JSM, in San Diego in a couple of weeks. If anybody's attending, please feel free. I'll be at we'll have a booth in the exhibition hall. I'll be there, so please feel free to come up if you have any questions or any thoughts on missing imputation and missing data analysis. So I'd like to thank you all for attending again. My email address is andrew.grannell@statsol.ie if you'd like to email me any questions or comments. You can also find me on LinkedIn and on Twitter there. I'll just take a moment there now to check up on any of the questions that have come in, so just give me a moment, please. Okay, just before you all go there, there's quite a lot of questions flooding in, so I'll have to get back to you all, because I'm aware of the time here. I'll have to get back to you all individually, but there's a quick question with a quick answer is how many imputations do you need to do? Now, I just ran 5 just for simplicity because I didn't want to be taking up a lot of time. 20 is the kind of the magic number when it comes to imputations. 20 gives you enough imputations to look at the distribution of the imputed values, and also to kind of run appropriate sensitivity analysis. You can do a maximum of 50 imputations in SOLAS and a minimum of 2. So just to round off there, thank you all again. We really appreciate the great turnout here over the last 6 webinars. I hope you've all found it interesting and helpful in your own work. And please feel free to contact me or meet me at JSM for any questions or discussions. Thank you all, and see you next time.